So in first experiment, we have seen how we can find coefficient of thermal conductivity of a good conductor. In this second experiment, we have to find thermal conductivity of a bad conductor. And the setup we use for this experiment is called Lee-Charlton's setup. Or this is also called Lee disk method. So can you tell me what are the examples of a bad conductor?
The plastic.
Yes. Okay.
Glass.
Plastic, glass,
Wood.
wood. Okay, and so on. So in this particular experiment, we will be using a wooden cardboard which is a bad conductor of heat, and we will be determining its uh, uh, coefficient of thermal conductivity. In last class also, we have seen that I have given you the definition of thermal conductivity, and we have seen that the magnitude of thermal conductivity, that is K, will be high for good conductors and K will be low for bad conductors. Because your Q, that is amount of heat transferred, is basically is directly proportional to the area of cross section, okay, and the amount of heat transferred through through any material is inversely proportional to the length of that material, length of that specimen, and this Q is also proportional to the delta T, that is temperature gradient. So if we remove temperature gradient, so if we remove this proportionality sign, then the total amount of heat transferred through a material, transferred through a sample, is equal to K A divided by D into delta T, where K is your coefficient of thermal conductivity, A is the area of cross section of this specimen, D is the total length of the specimen, and delta T is the temperature gradient across the edges, across the two sides. Okay. T1 minus T2 आपने सेल्स एक्सपेरिमेंट में लिया था, जो एक एंड पे कंडक्टर के एक एंड पे क्या टेम्परेचर है और दूसरे एंड पे क्या टेम्परेचर है. मोर इज द डिफरेंस, मोर विल बी द heat transfer. Similarly, more is the area of cross section, more will be the heat transfer, and less will be the length of the conductor, and more will be the heat transfer. And this all these proportionality sign are removed, and there is a constant which is called coefficient of thermal conductivity K. And of course, this value of this K will be high for good conductors and will be low for bad conductors. So in this particular case, in this particular experiment, we have to calculate this value of K for a bad conductor. So yes, we are going to have a value which is very low. Let's say 10 raised to the power minus 4 और 10 raised to the power minus 5 ऑर्डर में जो होगा. अभी आपने गुड कंडक्टर्स के केस में जो देखा, that was around 1. Okay, 1 into 10 raised to the power 0 means basically this was order. But in this case of bad conductors, yes, thermal conductivity decreases like this. It can come into the range of 10 raised to the power minus 4 or 10 raised to the power minus 5. Okay. So in this particular experiment, we will be using wooden cardboard as our specimen as our sample, of which we have to find the thermal conductivity. So before going into details of this Lee-Charter method, I will briefly explain. I will again start with Searle's method and then we will come back to Lee-Charter methods. Okay. So if you remember, in Searle's apparatus, there was a metallic rod. There was a metallic rod of copper, and with the help of steam, we have provided heat to one end. Okay. We have provided heat energy to one end, and this heat, after traveling through this rod by the means of conduction, this heat energy after traveling through this rod appears at end B, and at end B we have used water to dissipate this heat energy. Okay. And yes, we have calculated the amount of heat energy dissipated. You can say in this was heat in and this was heat out by the means of water. And if you remember, the heat traveling through this conductor, we have written it in amount of heat traveling through this conductor was given by K A by D and T1 minus T2. Okay. Whereas the heat energy expelled from the system with the help of water was equal to, okay, let's call this as Q, which was heat arriving at point B. This Q was heat arriving at point B. Now heat exhausting from point B was equal to M S and delta T. MS delta T, which was T3 minus T4, something like this. Okay. So this was your heat expelling out from the system, and we have equated these equations, these expressions, Ka D by T1 minus T2 equal to M into S into T3 minus T4 at the point of thermal equilibrium. We have first attained the point of thermal equilibrium, then we have equated these expressions to find out the value of K. Now, in this case, I can see the amount of heat transferred, through this conducting rod, through this thermal conducting rod, copper rod, was equal to K A by D T1 minus T2. Now, from the point of view of this K, if you can see, the magnitude of Q was large. The magnitude of Q was large because the value of K was large, because it was a good conductor. But suppose the similar kind of setup was used and this rod was made up of a bad conductor. If this rod was of a wooden material, if this rod was replaced by a wooden rod, then the value of K will be very low for that. As I have told you in earlier slide, that the value of thermal conductivity for a bad conductor lies in the range of 10 raised to the power minus 4 to minus 5. So in that case, if we had been using this same setup for a bad conductor, then the value of Q, the amount of heat transferred through this sample, was very low. And in that case, measuring the amount of this heat transfer by any means, would be practically difficult, would be practically impossible. So Basically what we have to do is, if our K is decreasing in case of good conductor, in case of bad conductor, if our K is decreasing, then we have to increase some other parameters so that our Q can be substantial in a manner so that it can be practically measured. So if K is going to a low value, then A should increase, right? Then the value of A should increase. Basically what I am saying is, I am saying if I have to replace the same setup, if I have to replace the same setup to check, to observe the value K value for a bad conductor, then what I can do is, my K is going to be decreased for a bad conductor, yes, but I can increase my A, area of cross section, I can decrease my D, and I can increase this temperature gradient, but practically this is not much feasible, because your T1 and T2 cannot exceed more than let's say 70 to 80 degree. ओके क्योंकि T2 तो रूम टेम्परेचर पे रहना है, तो उससे ज्यादा, उससे ऊपर अगर T1 को कितना इंक्रीज करोगे, 100 ले जाओगे, 110 ले जाओगे. So T1 and T2 has own restrictions, their own restrictions, but yes, we can increase the area of cross section and we can decrease the length of specimen so that the amount of heat transferred from a bad conductor in a similar methodology can be increased. The amount of heat transfer can be increased if we increase the area of cross section and if we decrease the length of specimen. So yes, what are the changes which we have to do in this Searle's experiment? Now instead of this morphology of sample, we will be using a sheet, a cardboard sheet like this one, whose thickness, let's say, is around 2 millimeter only, but its area of cross section is very large. So you can see that if I am increasing my A, I am decreasing my D, then of course the amount of heat transferred through this sample can be increased. The amount of heat transferred can be increased, and it can be increased up to such level so that it can be measured with a good accuracy experimentally. Okay, so the major difference from this Searle's experiment and in this Lee-Charton method is that in case of good conductors, yes, the area of cross section can be low, the length can be very large. Okay, but in case of bad conductors, our area of cross section has to be very large, and the distance of the length of the specimen, or you can say the thickness of the specimen, can be made very low, can be made very less. So, and all other things are more or less same from the physics point of view in both these experiments. The only difference is that we have changed the shape and size of our this specimen so that amount of heat traveling can be increased, and so such that this increased amount of heat energy transfer can be measured more accurately. Okay, so the setup for Lee-Charton method is something like this. There is a slab, metallic slab. There is a metallic slab. Let's call this as a slab A. Hollow hai. This is hollow from inside. And there are one inlet and one outlet for steam. And basically the function of steam here is to increase the temperature of this slab A. Okay, to increase the temperature of this slab A. Now we will introduce our specimen, which is in this type of shape. You can say this is your sample, and the upper portion of the sample let's call this interface as A. This A interface is actually acting as a heat source. So with the help of this steam, you are actually heating the slab A, and this heated slab A on the top surface of the sample, this will provide you the heat energy. This heat energy will travel through the sample through the modes of conduction. Yes, through the means of conduction, this heat energy from slab A will travel through the sample, and it will be passed to slab B, and it will be passed to slab B, and this will be solid. Okay, and this slab B. Okay, now again, if we see, the steam is coming out into this hollow chamber of slab A, and it is going out, but during the motion of the steam, the lower part of the slab A will get heated. Okay, and this heat energy will travel through the sample towards slab B. Both the slab A and slab B are of metal, and later on this slab B is hanging in the air, surrounded by the air, and you can say it is hanging in the air. It is just plainly hanging in the lab, and it is hanging in the air. But as you see, any material which is have higher temperature will lose its energy to the surrounding. Okay, through the Newton's cooling. You can say through the Newton's cooling. मीन्स वो ऑटो नेचुरली कूल कर लेगा अपने आप को, सराउंडिंग में अपनी हीट एनर्जी लूज कर देगा स्लैब भी. So this you can say as this slab B will act as heat sink. Okay, this will lose the heat, or you can say heat dissipator. Okay, so the overall thing is, actually what you are doing is you are providing heat. Okay, this is your sample. You are providing heat by using slab A, and this heat is being traveling through this sample. All of the heat energy will travel through the sample, and this heat energy will again be absorbed by slab B, will be received by slab B, and later on this slab B will lose this heat energy into environment. Okay, so after a particular amount of time, what will happen? The amount of heat traveling through this Q transfer will be equal to, this amount of heat traveling through this sample will be equal to Q heat lost to the surrounding by slab B. Okay, same हो जाएगा. This particular condition we will call as thermal equilibrium. Okay, so how we can achieve experimentally this thermal equilibrium? How we can confirm that the particular condition is now at thermal equilibrium? We can simply insert two thermometers at this point. Let's call this as T1, and at this point, let's call this as T2. Now suppose you are giving the steam to slab A. Now the temperature of slab A will start increasing. So that means your T1 is increasing. After some time, this sample will conduct heat to the slab B. And because of this conduction, the temperature of slab B also will also rise. So you will see, you will start noticing the increase in temperature of thermometer T2. But after some time, let's say half an hour or after 40 minutes, the amount of heat traveling through the sample, the amount of heat conduction traveling through this sample will be equal to the amount of heat released into the environment by this slab B. Okay. And at that point, you will see the temperature T1 and T2 will go to a constant value. They will not change. Okay. So that means if you after inserting the steam, after inletting the steam, if you measure the temperatures of both thermometers with respect to time, then after some time they will attain a saturation, they will attain a constant value. And at that particular point, you can say now the amount of heat transferring through this sample towards slab B is exactly equal to the heat lost by the slab B to the environment. And if you can relate this thing with the Sul's apparatus, this is actually a similar kind of thing. In that case, what you were doing is you were taking a rod. If I take that rod vertically, you were taking a rod and you were giving heat to this rod, and heat energy was being transferred through this rod with the help of conduction. But at this point B, there was a transfer of heat from side A, and moreover there was a water circulating through this coil, through this end, which was absorbing the heat energy. Okay, Q absorbed by water was equal to Q transferred through rod. Okay, in that case also the amount of heat transferred through this rod by the means of conduction was equal to the amount of heat energy absorbed by the water. Similarly, in this case also, what I am saying is the amount of heat transferring through this sample, traveling through the amount of heat energy transferring through this sample is equal to the amount of heat energy lost to the surrounding by slab B at the point of thermal equilibrium. So if I relate, if I can make the expression for this amount of heat transfer and amount of heat lost by the slab, then I can relate the value of K. We will see what will be the values of this, what will be the expression for this heat transfers. Okay, so this, as I told you earlier, this Q was equal to K A by D T1 minus T2, where T1 minus T2 is the actually temperature gradient across your sample, the temperature of this upper part of sample and temperature of the lower face of the sample. So this temperature is given by your T1 and T2, that is T1 and T2 are the temperatures at thermal equilibrium. So at point of thermal equilibrium, a constant amount of heat energy is being traveled through this sample, and the amount of the magnitude of that heat energy is given by, can be given by this expression. Similarly, if I want to find this Q lost, the amount of heat energy lost to the surrounding by the slab B, then this will be simple: Q M, the mass of the slab, S, the specific heat of the slab, and dt by dt, capital T by small t. This dt by dt is actually, you can say, is the cooling property of slab B. Cooling property of slab B. And it is also called coefficient of Newton cooling, that is different thing. Okay, so this is called cooling property of slab B. dt by dt, if I talk about this dt by dt, then this means, this is actually, this means more is the value of dt by dt. More dt by dt is actually nothing, it is how fast can slab B release the heat energy into surroundings. Okay, This dt by dt is nothing. It just tells you how fast this slab B can release the heat energy into environment. More is the value of dt by dt, you can say faster is the cooling. Faster is the cooling. Less will be the value of dt by dt, you can say slower is the cooling. Okay, so yes, we also have to find this value of dt by dt, and by experiment we will see how we can find that. But if we have this value, as I will provide you, as will be the specific heat of the material used to make slab B, m is the total mass of the slab B. Okay, so this will be total your q lost, heat lost, where on the left hand side you can see the amount of heat transferred was equal to k a d t1 minus t2. In both of these expressions, we can find value of a, we can find value of d, we can have value of t1 t2 at equilibrium position, at steady state condition. We can measure the mass of this slab B, we can have value of s, we can have dt by dt. So we have all the parameters, and we can say that the value of k, okay, so this value of k was equal to value of q was equal to k a by d t1 minus t2, and value of q was equal to m s dt by dt. So if I relate these expressions, then it will become like this. At point of thermal equilibrium, you must write this equation at point, you must write this line at point of thermal equilibrium only. At point of thermal equilibrium, or you can say at steady state. Steady state is a condition when temperature of both the thermometers will remain constant with respect to time. So if I equate these expressions, this can lead us to the value for k. Yes, value of k will be m s d by a divided by t1 minus t2 multiplied by dt by dt. Okay. Okay. So in this method, I can find the value of k if I have the value of dt by dt. So in first part, okay, this experiment is basically divided into two parts. In first part, okay, first I will show you the setup, then we will again come back to this page, and we will see what are the steps. Okay, so what we were doing, we were finding the coefficient of thermal conductivity of a bad conductor by this Lee and Charlton's method. So see, this is your setup. This is called Lee disc apparatus. There are two circular discs of same diameter. There are two circular discs of same diameter but of variable thickness. Okay, ये ऊपर वाला ज़्यादा बड़ा है, नीचे वाला डिस्क छोटा है, and ऊपर वाला डिस्क जो है, that is hollow from inside, and there are two inlet. So there are inlet and outlet for steam. So steam will be coming from this direction. Okay, and steam will be circulating in this chamber A. The upper chamber I am calling as chamber A. The steam will be circulating, and hence it will start increasing the temperature of this chamber A, and this is the exit option for steam. But yes, the passing the steam from this chamber A will certainly increase the temperature of this chamber A. Now this increase in temperature of chamber A basically will result in the flow of heat energy through this specimen. You can see a cardboard sheet is sandwiched between these two slabs A and B. This cardboard is actually the specimen, is actually the sample of which we are trying to find the value of thermal conductivity. This cardboard, which is inserted between these two slabs. Okay, so yes, after acquiring a particular temperature or after gaining a heat energy from this steam, this slab A will act as a heat source, and this heat energy will travel towards this slab B through the modes of conduction, through this cardboard sheet, through this bed conductor by the mode of conduction. And the amount of heat energy received by this slab B will start dissipating into the environment, into the neighborhood. जो उसके बाहर एयर है उस पे वो डिसिपेट करना शुरू कर देगा, उसमें वो हीट रिलीज करना शुरू कर देगा. तो एक टाइम ऐसा आएगा जिस पर्टिकुलर टाइम में आपका द अमाउंट ऑफ हीट एनर्जी ट्रेवलिंग थ्रू दिस cardboard sheet towards downward towards slab B will be exactly equal to the amount of heat energy lost by this surrounding by this slab B, and that point is called thermal equilibrium. Okay, so we will see. So you see, this is a shape and this is the thickness of your bed conductor. This is your sample of which you have to find the thermal conductivity. So in this experiment, we will be requiring this steam generator, a hot plate to boil the water so that it can generate steam, and this steam will be passed through this slab A, and this is your sample bed conductor, wooden cardboard sample. We will be requiring thermometers, a screw gauge, and a vernier caliper. A vernier caliper to measure the diameter of this plate, and screw gauge for measuring the thickness of this sample, and stopwatch to find the cooling curve that we will see later. Okay, so the first procedure is you can take water into the steam chamber. You can start increasing the temperature of hot plate. Okay. And okay, you can suspend this setup, this Lee-Charlton method setup, into a stand by modes of thread. This is your slab B. First you have to hang this slab B, then you can place your specimen onto it, then you can place your specimen onto it, and then you can place your slab A, which have openings for steam in and steam out. You can insert thermometers. These slabs have drilled holes for these thermometers. You can insert T1 and T2 into this slab A1 and slab A and slab B. Steam in, steam out. So this, from this steam chamber, the steam will come and circulate in this chamber A, and it will heat this chamber A. And there is the steam will escape after heating this chamber A. Steam will escape into the bucket, into the waste bucket. Okay, this is actually your again a different angled photo of your setup. You can see this is your slab B. The lower slab is slab B. There is a sample, cardboard sample, sandwiched between this slab A and slab B. These are steam inlets and steam outlets, and this whole thing is hanged on the stand by the means of threads. Okay, this is again a new photo, different angled photo. इसमें steam generator भी साथ में रखा हुआ है. On this steam generator, there is a knob which you can increase the temperature of this water so that to increase the flow of steam, to increase the you can say flow of steam, how much steam we are trying to pass through this chamber A. This steam flow can control by the temperature of the boiling water. Okay, so for procedure, first of all you have to weight the slab B and you have to determine its mass M. You can easily do it with by using a weighing balance. Second, you have to measure the experimental to measure the diameter of this disc D of this sample with the help of vernier caliper at number of places. Okay, वो थोड़ा सा यूनिफॉर्म नहीं होता है उसका डायमीटर, तो इसीलिए दो तीन प्लेस पे उसका डायमीटर अलग लेके you can take the mean diameter, and from the help of diameter you can find radius and you can find area of cross section of this sample. Then you have to find next you have to find the thickness of this sample with the help of a screw gauge. Now, as thickness is very low, instead of finding it with the help of vernier caliper, we will go with the screw gauge, because screw gauge is more, you can say, accurate, or you can say this has low least count. Okay. So thickness will be measured by screw gauge, while the diameter of this disc was measured by vernier caliper. Then after that, you have to hang the slab B. You have to hang the slab B, and you have to place your experimental disc D. You have to place your disc, cardboard disc, uh, onto this slab B, and then you have to place your slab A on the topmost, on the top. So you have to arrange this apparatus with experimental disc D sandwiched between A and B slab. After that, you have to pass the steam through slab A, and after some time, let's say after half an hour, you have to record the temperatures T1 and T2 at regular intervals of 2 minutes or 3 minutes. Okay. Now actually what you are trying to do, you are seeing how this temperature T1 and how this temperature T2 is behaving with respect to temperature. Okay. When after some time T1 and T2 will become constant, then you can say the steady state is reached. The thermal equilibrium is reached, and these are the values of T1 and T2 which you will have to use in your formula. Okay. Now the second part is again, I will go to my notebook. See, up to this point, what you have to do is you have find M in this formula. You have find M. You have S. S is given. You have find D. You have find A, and you have find T1 minus T2. Or you can say, you have completed. You have find this value of heat transfer. You have find this value of heat transfer. You have you have A, you have D, you have T1 minus T2, you have M and S also. Now to find this dt by dt, let's say the steady state temperatures are 90° and 80°. Let's assume, okay, 90 and 70°. So actually, as we have seen in previous slide, at point of thermal equilibrium, the amount of heat energy transferred was equal to amount of heat energy lost by this slab B. So the heat energy lost by this slab B at the point of thermal equilibrium, will be given by ms dt by dt, where dt by dt at thermal equilibrium, where T is equal to T2, where T is equal to T2. T2 was your temperature of thermometer at steady state, at thermal equilibrium. So for finding this value of dt by dt, what we will do is we will disassemble all these apparatus, disassemble all these slabs. We will just take slab B. Okay, we will just take slab B, and we will start heating this slab on the hot plate directly with a thermometer in it, which is called T2 thermometer. Okay, we will start heating this slab B on a hot plate directly, and we will be observing our temperature continuously, and we will go up to, let's say, T2 plus 10°. Okay, we will heat this slab B alone. Up to a temperature which is greater by 10° than this equilibrium temperature T2. Now I will tell you the logic behind this actually, but we will first heat this slab B alone on the hot plate directly up to a temperature whose value is 10 degree more than the T2 value, where T2 value was your equilibrium temperature. Then after that we have slab B at temperature, equilibrium temperature plus 10 degree. Okay, and we will with time we will observe its temperature. Let's say 0 degree पे, let's say 80 degree था, 30 सेकंड में कितना टेम्परेचर लूज हुआ है, कितना टेम्परेचर डिक्रीज हुआ है स्लैब बी का, लेट्स से 75 हुआ है, 60 सेकंड में लेट्स से 72 हुआ है, 90 सेकंड में लेट्स से 68 हुआ है. So we will see how the cooling of this slab B is taking place, how the cooling of this natural cooling of this slab B is taking place. So we have, as we have increased the temperature of slab B by 10 degree more than the equilibrium temperature, you can say, okay, Newton's law of cooling says that the temperature of a body will decrease in environment naturally like this. Well, like this is T, this is T, this is time, this is temperature. So you will obtain a cooling curve, you can say a cooling curve of slab B like this, something like this. And of course, as we have taken, the temperature of this slab B is 10 degree more than the equilibrium temperature, and we will be observing up to 10 degree less than the equilibrium temperature. Okay, so let's say agar equilibrium temperature 70 degree tha, so we will be going from 80 to 60. We will be observing how this slab B, how much time it is taking from going to 80 degree to 60 degree. So let's say this was your 80 degree, and let's say this was your 60 degree. So this is particularly a cooling curve of slab B, and at point of thermal equilibrium, यहाँ पर कहीं पे, this will be your T2. Okay, because this was your T2 plus 10 and this was your T2 minus 10. So this is, if this is your T2, then what I have to do is I have to draw a tangent. I have to draw a tangent to this point T2, and it will be something like this. Okay, वो थोड़ा पास होना चाहिए था उसके. I have to draw a tangent at point T2, and the slope of this tangent, will give me the value of dt by dt. Of course, at t is equal to T2. So इस ग्राफ से हमने क्या देखा, हमने देखा कि भाई टेम्परेचर, थर्मल इक्विलिब्रियम का जो टेम्परेचर है T2, उस टेम्परेचर पे कूलिंग कैसे होता है, कितना हीट लॉस करता है सराउंडिंग पे, एंड दिस अमाउंट ऑफ दैट हीट लॉस is directly proportional to this quantity dt by dt. So this dt by dt is actually the parameter for calculating the amount of heat lost to the surrounding. Okay, and the total amount of heat lost will be given by the this parameter dt by dt into mass of this slab B into specific heat of this slab B. And you can see more is the numerical value of this dt by dt, more is the numerical value of this dt by dt, more will be the amount of heat lost. Okay, this is obvious. अगर जल्दी से लूज कर जाता है वो अपना टेम्परेचर, that means amount of heat energy lost per second is more. So in this particular experiment, the first part of this experiment was to find the thermal equilibrium conditions, this M, S, D, A, and the thermal equilibrium temperatures. Second part of this experiment is to disassemble this apparatus, and you have to just heat the slab B, and you have to see the cooling curves. You have to plot the cooling curve of this slab B, in which you will be searching, you will be finding the slope of the tangent of this cooling curve, so that you can calculate the value of Q lost, or you can calculate the value of this parameter dt by dt. Now, after this, as you can see from this formula, we have all the values. We have M, we have S, we have D, we have A, we have T1 minus T2 at equilibrium, and we have the dt by dt value of this slab B, which is the indicator of, you can say, heat dissipator. Okay, and after inserting the values of all these parameters, or after inserting all the observed value of these parameters, we can easily find the value of K. And in this particular case, your value of K for a cardboard generally lies in the range of 10 raised to the power minus 4. But okay, let's say I have to give some theoretical value. You can say, so this is my value which you should obtain if you obtain the slope of this tangent carefully. Calorie per gram per second per centigrade. Okay, this type of unit. Okay, so this K will be equal to, K should be equal to this much. So as you can see, this will be 0.00035, right? ऐसा ही कुछ है ना? हाँ. So see, this is the value of bad conductor, conductivity of bad conductor. While in case of good conductor, this value was approximately 0.921. So you can see from the values of thermal conductivities how these two different type of conductors have actually very different values of K. Okay. So I will again come back to my presentation. In this, okay, यहाँ तक हमने किया था. Now in fifth point, that is the second part of this experiment, you have to heat the slab B alone until its temperature is about 10 degree above the steady state temperature T2. Suspend this disk B with disk D on top of it and allow it to cool. Okay, I will again come back to एक ये point अभी बताना है. See, in the case of experiment, during the experiment, in the case of achieving thermal equilibrium or steady state, the condition were like this. This slab B was losing its heat energy. This slab B was losing its heat energy through the bottom layer of this slab B and through the curved surface area of this slab B. Through the curved surface area of this slab B and the bottom part of this slab B. But the upper part of this slab B was restricted with a bad conductor. This slab B was not losing heat energy from the upper surface of this slab. This slab B was only losing the heat energy either through the curved surface area or through the lower part of this slab B. So to maintain the same rate of heat lost, so that our value of dt by dt will be good, what we will do is, during measuring this cooling curve, we will insert the specimen disk again on the top of it, so that the heat lost by the slab B during the first part of experiment, that is during the thermal equilibrium achievement, will exactly be equal to the finding this cooling curve. कूलिंग कर्व जब फाइंड कर रहे हैं उस टाइम पे भी आपका जो स्लैब है, वो स्लैब जो हीट लॉस करेगा वो भी केवल आइदर साइडवेज से करना चाहिए या लोअर सरफेस से करना चाहिए. अपर सरफेस पहले वाले पार्ट में भी ब्लॉक्ड था एक बैड कंडक्टर से, तो सेकंड वाले पार्ट में भी ब्लॉक कर रखना है. तो कैसे ब्लॉक रखेंगे? हीट द स्लैब बी अलोन until its temperature is about 10 degree above the steady state temperature. Suspend the B, 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 suspend suspend this B with a disc D with insulating sample on top of it, not insulating, bad conductor sample on top of it, and then we will allow it to cool. After that, we have to note the temperature T of the metal slab B after every 30 seconds till its temperature falls to 10 degree below T2. Actually, what we are doing is we are trying to find how this slab B is cooling in the vicinity of this temperature T2. उसको 10 डिग्री ऊपर तक हीट करके उसके 10 डिग्री नीचे तक उसको ऑब्जर्व किया कि कैसे कूल कर रही है, एक कूलिंग कर्व ऑब्टेन किया, उससे उसका टेंजेंट ड्रॉ करके T2 पॉइंट पे और वहां पर स्लोप निकाल लिया उसका. Now you have to plot a graph with time along x-axis and temperature along y-axis. This will give you a cooling curve. Draw the tangent to this curve at t is equal to T2 degree and determine the slope of the tangent. This will give you the dt by dt value. This dt by dt value will be used in this formula. ये सब सेम चीज वही लिखा है जो मैंने अभी एक्सप्लेन किया था कि क्या क्या होगा आपका. Heat gained per second to slab B will be equal to the heat lost per second by slab B. So this formula you will be using for this calculation of K. Observation table ऐसे बनाना है. Specific heat of material will be given, mass of slab will be given to you, diameter you have to calculate from the website, circular area of disk you have to calculate by using diameter of the disk, thickness निकालना है स्क्रू गोज से, स्टडी स्टेट टेम्परेचर निकालना है. इससे पहले एक और ऑब्जर्वेशन टेबल आ जाएगी which will contain time T1 and T2, and with respect to time you will be measuring T1 and T2, and जिस भी पॉइंट पे जिन भी दो रीडिंग्स के लिए या तीन रीडिंग्स के लिए T1 और T2 कांस्टेंट हो जाएगा, then we will consider that now thermal equilibrium is achieved or steady state is achieved. We will take those values of T1 and T2 in the formula, and this will be your last observation table. इसमें क्या है, टाइम है और टेम्परेचर ऑफ बी है, उसको हीट कर रखा है 10 डिग्री ऊपर पे, और फिर उसको हीट कूल होते वक्त उसका टाइम के साथ उसका टेम्परेचर नोट करना है. एंड दिस ऑब्जर्वेशन टेबल will yield you to cooling curve, and from that cooling curve you have to find the tangent at point T2 and then you have to find the slope of that tangent. ये ऐसे किया जो इन्होंने ना. Suppose this is your cooling curve and you have to find slope of this tangent drawn at point P, and this slope will give you the value of dt by dt, and with the help of this formula you can find the value of K. If you are taking the mass in grams, okay, if you are taking the mass in grams and specific heat in the CGS units, then the value of K will come out to in the calorie per second per centimeter per centigrade. Okay, अगर उसको kg में कन्वर्ट करके और उसको उसमें करते हो तो फिर वो जूल्स पर सेकंड में आ जाएगी. बट यस, थर्मल के एक्सपेरिमेंट्स में जनरली सीजीएस यूनिट ही यूज किया जाता है और ये सब कैलोरी वगैरह में ही रखना है. ओके, रिजल्ट लिखना है. एक्चुअल वैल्यू अभी मैंने बताया 3.5 into 10⁻⁻⁴ यूज कर सकते हो एरर कैलकुलेट करने के लिए. इसी के आसपास आएगा आपका फाइनल वैल्यू. इसकी जो बैड कंडक्टर्स का थर्मल कंडक्टिविटी आएगा, that should come in the range of 10⁻⁴ to -5. Okay. From the same website you can see in Lee-Charlton's method. Click on this. ये देख सकते हो, इसी को देख के फिगर बना सकते हो, या इंटरनेट पे भी काफी पड़ा हुआ है इसका मटेरियल. ये भी वही सब लिखा हुआ है कि कैसे हीट ट्रांसफर हो रहा है टॉप मेटल डिस्क से बॉटम मेटल डिस्क की तरह. मैं इसको चैम्बर ए और चैम्बर बी बोल रहा था. तो दिस हीट विल बी ट्रांसफर्ड थ्रू दिस पोरली कंडक्टिंग सैंपल टुवर्ड्स द बॉटम मेटल डिस्क. वो सब इसमें लिखा है इस टाइप से. प्रोसीजर है, ये सब आपको लिखने में और समझने में हेल्पफुल होगा, इसीलिए मैंने लिखा है. वर्चुअल ये लैब, इसकी ऑब्जर्वेशन लेने के लिए स्पेसिफिक हीट ऑफ द मटेरियल ऑफ स्लैब बी इज गिवन. ओके, मास ऑफ द स्लैब इज डायरेक्टली गिवन. यू हैव टू कैलकुलेट द डायमीटर ऑफ लीड डिस्क. इस पे क्लिक करेंगे, इसमें ऑब्जर्वेशंस आने लग जाएंगे आपकी, जैसे लास्ट क्लास में किया था सेल्स के लिए. उसमें कैलकुलेट डायमीटर ऑफ लीड डिस्क कर सकते हैं. उस डायमीटर से रेडियस निकाल सकते हैं, देन एरिया ऑफ क्रॉस सेक्शन निकाल सकते हैं. Similarly you can find the thickness of this lead is by this, and after that what you were supposed to do is you were supposed to start the steam and measure temperature on both the thermometers. तो उस पे क्लिक करोगे and it will start giving you values at 3 minutes, at 6 minutes, at 9 minutes. So you will be making an observation table with time, with temperature T1 and with temperature T2. After that you will be observing a cooling curve of metal slab B. हीट कर दिया होगा, उसके बाद कूलिंग कर्व जब देखेंगे आप इस तरह से दिखाई देगा कि at 0 seconds the temperature of this slab B was 82.5. ये ऑब्जर्वेशन टेबल में लिखना है. 30 सेकंड में इतना हो गया, 60 में इतना हो गया. तो इस तरह से ये कंप्लीट आपको वो दे देगा ऑब्जर्वेशन टेबल, एंड दैट ऑब्जर्वेशन टेबल विल बी हेल्पफुल फॉर ड्राइंग द कूलिंग कर्व. उस कूलिंग कर्व पे टेंजेंट ड्रॉ करेंगे T2 पॉइंट पे, उसका स्लोप निकालेंगे, दैट विल गिव यू द वैल्यू ऑफ dt/dt. ओके, इस पे जाके सब ऑब्जर्वेशन अपलोड करना है. बेसिक इंफॉर्मेशन पूछेगा, उसके बाद फिर कैलकुलेटेड सर्कुलर एरिया ऑफ डिस्क ए पूछ रहा है, डी पूछ रहा है, टेम्परेचर ऑफ बोथ थर्मोमीटर एट स्टेडी स्टेट पूछ रहा है, T1 और T2 का वैल्यू ले रहा है, एंड एंटर स्लोप ऑफ टेंजेंट ऑफ कूलिंग कर्व ले रहा है. क्या स्लोप आपका आया है उसमें ग्राफ से. उसके बाद डायरेक्टली रिजल्ट पूछ रहा था, थर्मल कंडक्टिविटी ऑफ बेड कंडक्टर ऑब्टेन एक्सपेरिमेंटली इज दिस वन. ओके, नेक्स्ट उसके बाद ये अपनी ऑब्जर्वेशन टेबल अपलोड करने के लिए बोलेगा. ऑब्जर्वेशन टेबल, ग्राफ एंड कैलकुलेशंस, ये सब एक पीडीएफ में बना के इसको अपलोड कर सकते हो. ओके, सो इफ आई कम बैक टू माय दिस नोटबुक, तो अगर अब आपको इसमें समझ में आया है. ओके, so this was actually I was talking about, in case of Searle's experiment the area of cross section was low. In Searle's experiment area of cross section was low and the length of the specimen was high, so that amount of heat transferred Q will become low. But in case of bad conductors, as the K value is extremely small, so to increase the value of Q, what we have to do is we have to increase the area of cross section of the sample and we have to decrease the length of the specimen, which you have seen that we have done successfully. We have taken a cardboard of a large cross section area and of very minimal thickness, so that the amount of Q is such that it can be measured experimentally. I think it's enough. I hope आप लोगों को ये समझ में आया होगा.